class. Today we're going to be going over section 2.2 for college algebra. There's a lot in this section, so it's going to be a little longer of a video. We are going to look at increasing, decreasing, and constant intervals, relative extrema, how to determine even and odd symmetry, and piecewise functions. There's a lot in this section for sure. So I'm going to kind of run through it fairly as quickly as I can. So we'll see how we go here. So when you're figuring out your increasing, decreasing, or constant intervals, we want to read our graph like we read a sentence in English. So left to right. At least that's my left to right. I'm not sure if I mirrored with you. So when we read a graph, we want to go from this direction and go that way. So if I'm going from left to right and our graph is increasing, that's an increasing interval. If I'm going from left to right and it's decreasing, we've got decreasing, and if it just stays flat, then it's a constant interval. A couple things to note with these intervals. Intervals are always x values or values from our domain, and endpoints are never included. I can go over why really quick. Basically, if I'm increasing and then it's like it stops increasing, well, it stops increasing, so we wouldn't include that point because at that point we're not increasing anymore. Why endpoints aren't included with constant intervals, I'm not sure. Maybe because at that point we stop and we're no longer constantly going in the same direction. But in any case, endpoints are never included. So I'm going to use some highlighting here. Let's see. So let's do green for increasing intervals. So increasing intervals from left to right, we're going to have this section here. Oh, it's hard to make that happen. On this graph, on the next graph, we've got an increasing interval here, so we can see how it's going up from left to right. For our decreasing interval, if it goes down from left to right, it's decreasing. Again, I've got another down value there. And for part A, very leftmost part of the graph is a little tricky because the arrow is pointing up. So a lot of students think, oh, it's increasing. But if you look at, and if you like trace, physically put your finger or your pencil on the graph and trace it as you go from left to right, if your finger is moving downward, it's decreasing, even if that arrow is pointing up. So be really careful about that. All right, and then let's do, an orange. Orange for constant, so this would be a constant interval here. So we have, let's go back to our pen here. Increasing intervals, so that green portion that I highlighted goes from 0, and I'm using interval notation, which I covered in my previous lesson in 2.1. 0 to 2. Our decreasing intervals, the first one goes from negative infinity all the way to 0, and the second one goes from 2 to infinity, so those two purple sections. And in this case, for part A, we don't have any constant intervals. Similarly, for B, my increasing interval goes from 0 to infinity. Again, we see that open circle, but with these kinds of intervals, it doesn't matter if we have open or closed circle. It always is not including our endpoints. Decreasing, I don't have any, and my constant interval goes from negative infinity all the way to 0. Again, I know it's a closed circle there at the end of our constant interval, but we do not include endpoints for these. It's one of the hardest things to remember. All right, moving on. Talking about relative max and relative min, so relative extrema. There's two different types of extrema. We have absolute extrema and relative extrema. An absolute extrema would be like the highest point on your graph forever. Nothing will ever get higher than that on the graph. And if you notice in this graph, it keeps going up and up and up and up and up forever. So there's no, just a little note here, no absolute extrema for this example, for this graph, because it keeps going up and up and up forever. It keeps going down forever. So there's never going to be a highest or an absolute lowest point. But relative to certain parts of our graph, we have max and mins, specifically where our function changes direction. So this, let me get my highlighter, handy dandy highlighter here. this portion here and this portion here are going to give me a relative max and min. Now, if it is like bottoming out and then coming back up, that's going to be a minimum because it's a lower point at that part of our graph. So relative min would be the point -1 and -2. Now, I wrote, so this is not interval notation. This is a coordinate point. Some textbooks, actually a lot of textbooks, if they ask you for the relative min, sometimes they only want the y value, which in this case would be -2. For my class, I'm all right if you just give me a coordinate, but I think when you're doing problems in your book and you check your answer, they may only give you the y value. All right, and then relative max, again, my coordinate would be 1, 2. So this, again, is a point, not an interval. Or if you wanted only y value, that would be a +2 for our relative max. All right, moving on, we're going to look at symmetry, so even and odd functions. An even function is a function that's symmetric to the y-axis. Now, these pieces, so even, we have a point xy corresponds always to a point -xy. So if I negate the x value, the y value is going to stay the same. That'll reflect that over the y-axis for me, like you see in the graph. An odd function, and I'm skipping the middle one for a second, an odd function is something that's symmetric to the origin. So there's a couple ways to describe that. You can describe it as a reflection over the y and x axis if you like to visualize reflections. And if it becomes where it is like that. Let me think how to explain this. So the whole thing, this example here, example C, the graph is actually both curves. If I took both parts of the curve and I flipped them over the y-axis and then flipped them over the x-axis again, I would end up with the exact same graph that I had. Another way to think about it is every point xy, if I go to the origin, 0, 0, and then in the very opposite direction, the same amount, I will land on another point. So that's another way to think about a symmetry through a point, specifically the origin. So here I have the point xy, sorry, x comma y would be symmetric to -x, -y. Now this one is symmetric to the x-axis. It's not labeled as even or odd. So we are going to not write anything there, but I mean, it's symmetry. It's just not even or odd. So down here, we can determine if a graph is symmetric to the x-axis, y-axis, oops, I have a typo there, or the origin by graphing. We haven't really done sideways parabolas yet, but when you have an x and a y squared instead of a y and an x squared, it's still a parabola, it's just sideways. So I'm going to quickly just go over what this would look like. I'm doing a rough sketch here. It's fairly rough. That would be symmetric to the x-axis. And then this parabola, so x squared minus 1, we have something like this. Again, it's a fairly rough sketch. This would be symmetric to the y-axis, which makes this an even function. And then x cubed, again, really rough sketch. I know I'm not going through my exact points here. Actually, I really should. I'm sorry. So I have 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. This is the 0.28. And then something like this. This is -2, -8. So I do want to show you how these points and symmetry line up. So if you notice, so this is an odd function symmetric to the origin. If you notice those points, that 0.28 has a corresponding point -2, -8. So if I negate the x, the y is going to turn -2. Let's see, 1, 2, 1, 2, 3, 4. So this point at 2, 3 would have a symmetric point at -2, 3. So if I negate the x with an even function, the y stays the same. That's a better graph for you. Okay. So now let's look at, and I'm going to kind of skip some of this here because I've paraphrased down at the bottom. So we're skipping to the bottom of the next page. You can go back and fill in the notes. Let's look at how to determine whether a function is even, odd, or neither based simply on algebra. So an even function, remember, if I have the point x, y, I'm going to have the point negative xy. So if I negate the x, the y stays the same. What I have here in function notation is f of negative x. So if I replace x with a negative x, which is the same as negating the x, it's going to be the same as the original value because the y's stay the same. So what I can do is I can find f of negative x. I'm going to have negative x cubed minus 6 times negative x. So we went over evaluating functions like this in the previous lesson. Now, negative x cubed, I have 3 negatives, so that's going to be negative x cubed and then a positive 6x. Now, this is not equal to f of x, so it's not even. If it were even, we would have ended up with the same function that we had before. Now, an odd function, if I negate the x, the y changes sign. So now, if I look at negative f of x, so if I take the original function and I distribute a negative through, and I get negative x cubed plus 6x. If those are the same, so negative f of x was the same as f of negative x, then this is an odd function. That means what happened is when I negated the x value, the y value ended up being the opposite sign as well. All right, a couple more examples here. I'll just do one more example since I don't want this lesson to be too long. Okay, so number 2, we've got g of x. So I'm going to start by doing g of negative x. Again, remember, if g of negative x equals g of x, then it's an even function. If g of negative x equals negative g of x, then it's an odd function, and you'll want to memorize those. So I'm going to replace all the x's with a negative x. 4 negative x's turns positive, x to the 4th. And then minus 2, and then negative x squared is a positive x squared. So I'm going to rewrite that as x to the 4th minus 2x squared, which is the same as our original function, which means this function is even. And I actually don't want to do any more work because if it's even, it's not odd, and I'm done. I'm going to leave number 3 for you guys to work on. You can check your answer on the calendar. If it's not even, make sure to check to see if it's odd. Sometimes it's neither, hint, hint. So you can play with number 3 there. All right, our last part to this lesson is piecewise functions. So piecewise functions are really useful in real life because sometimes if we're modeling something in real life with a function, one function won't really do it for the whole model. Sometimes we have to use pieces of different functions for different pieces of our model. So for example, telephone company offers the following plan. You pay $20 a month and you get 60 minutes. And additional time costs $40 per minute. So you can see we have a function c of t equals, and then there's 2 options. There's one, if your minutes are between 0 and 60 minutes, then you just pay $20. If your minutes are more than 60, you pay $20 plus 40 cents for each minute above 60. So that's why, so minutes more than 60. That's why they did t minus 60. So you're not paying 40 cents for all your minutes, just the ones above 60. So if I want to find c of 30, so that means I'm talking for 30 minutes. How much is that going to cost me? Well, 30 is within this first, so t equals 30 is in that first domain. So I'm going to have just 20 or $20. I'm not going to plug it into the second one because the second equation that we have only counts for minutes that are more than 60. For example, when c is 100, or sorry, c of 100. So when t is 100, I would then be using the second formula. So 20 plus 0.40 times 100 minus 60, and I can solve for that. We end up getting $36. So you're not going to plug these into both parts. You're going to figure out which one does it correspond to and just use that piece. Right, last example, we're going to graph a piecewise function. Now this definitely takes some practice, and I have some extra videos on graphing piecewise functions on our calendar that you can use if you need help. So the first thing I'm going to do is I'm going to look at my domain restrictions. I have the first function only happens when x is less than or equal to 1. So I'm going to put a dashed line here, and this is when x equals 1, because that's where my formulas or my equations are going to split. So for x less than or equal to 1, so if I have going this direction, s less than or equal to 1, I'm going to have the function x plus 2. So I can graph the function x plus 2. Let's see, I add 2 to my 0, and then it has a slope of 1, a positive slope of 1. So it's going to look like this. I'm counting by ones on my axis. Make sure to always show me at least 1 or 2 numbers on your axis so I know what you're counting by. And then if you notice, if it's less than or equal to or greater than or equal to, it's going to be a closed circle where it ends. So I want to keep going until I hit that dashed orange line that I drew. And it's going to be a closed circle because it was including, it was less than or equal to. Now I want y to equal 4. So if it's less than or greater than, it's going to be an open circle. And the 4 corresponds to this side of the graph when x is greater than 1. So y equals 4 is just a horizontal constant function. So 1, 2, 3, 4. I'm going to start with an open circle because it's just greater than 4, not actually including 4. And draw it that direction. All right, and then that's it for the piecewise. So piecewise, I know this is a basic example, and it does take some time to get used to all those different pieces, but you can do it. I believe in you. All right, and that's the end of our lesson.